Everybody can see that now? All right, so what we have in series will be this. This will be a circle with a sine wave in it. That designates an AC signal source. And with an AC signal source, we will have 1, we will have 2, and we will have 3 resistors. We'll have an R1, R2, and an R3. And we will connect it like so. Typically, we'll put the ground connection there. We will have a point A, we will have a point B, we will have a point C, and we will have a point D, and this will be a point G for ground, let's say. And the resistances will be 180 ohms, which you have the resistor for, 330 ohms, which you have the resistor for, and 120 ohms, which you also have the resistor for. Now, you've seen this circuit before. We've analyzed this with DC. With AC, everything with respect to Ohm's law that you have learned holds true for AC as well. So I'm going to set up a VIR table, like so, and we'll do 4 rows for the 3 resistors. Remember, R1, R2, R3, and totals goes over here, and we will have VI and R. And so the resistors you fill in 180 omega, 330 ohms, 120 ohms, and the source we're going to use will be an AC source, and I'm going to give you a separate sheet for analyzing that. The AC signal, we're going to do this way. I'm going to use a separate piece of paper here. And I'm going to propose an AC source that looks like this. I'm going to bring this down a little bit more to here and give us something to focus on here. Okay, now that's focused. So let us say for a moment, you are going to be shown this particular waveform. It will be a sine wave. And I'm going to tell you that given something like this and something like this, this will be, and then we'll go ahead and do it this way. 1, 2, 3, oops, almost there, to here and to here. Okay, best as I can draw it. Let's say our V scale is equal to, the vertical scale will be equal to 3 volts per division. And let's say our H scale, horizontal scale, is equal to, I want to say 120 microseconds, okay, per division. You are tasked with interpreting this waveform based on how I've drawn it to give us the following values. We are looking for V peak. We are looking for V peak to peak. We are looking for VRMS. We're looking for V average. We're looking for T, which is period. And we're looking for F, which is our frequency. So those would be the things that we're looking for based on this particular waveform. Now, that being said, I have a vertical scale of 3 volts per division, horizontal scale of 120 microseconds. Are your calculators ready? Okay, so for V peak, I'm going to ask Jacqueline, can you give us the V peak? How would you determine V peak based on how I've drawn this picture? Go ahead and verbalize.
You would count the squares to your highest point, and then you would multiply that by your V scale.
Excellent. And from where do we begin our count?
The 0 line.
From the 0 line. So here is our 0 volts line. Our 0 volts line is always going to be in the center of your oscope. And as your classmate says, we will start counting from here up to the positive peak, the number of squares. And how many divisions do we count here, Jacqueline?
2.
It looks like 2, best as I can draw it. It looks like 2 divisions. We're going to multiply this by the vertical scale. So we have 2 divs times 3 volts per div is equal to some volts peak. And that calculates to be what value volts peak, Jacqueline?
6 volts peak.
And how many of you agree that we should have a 6 volt peak waveform based on her interpretation? Looks like a bunch of thumbs up. And if you notice here, the way I've written it, 2 divs times 3 volts per div, what happens in the mathematically is that the divs cancel out, and that's why you're left with volts. And since we're looking for peak, it's written as 6 volts peak. Good. The next one, Brad, if I have 6 volts peak, can you verbalize how we determine volts peak to peak? How do I do volts peak to peak?
So you would go from the 0 scale from the top to the bottom and get the total, which would be 4.
Okay, it looks like from the tippy top of the positive peak all the way to the bottom of the negative peak, we have a total of 4 divisions. Yes, 4 squares. And what do we do with those 4 divisions?
Divided it. No, you multiply it by the what is it? The VPP.
We're looking for VPP. Take a look at my diagram. And what did your classmate do before? She took 2 divisions and multiplied it by the 3 volts per division, which was our vertical scale. That's what she did. So you're taking 4 divisions. What are you going to do with those divisions? You're going to multiply it by what?
By the V scale.
Yeah, the V scale. And that would be
3
volts per division. Everybody repeat. Say 3 volts per division. 3 volts per division.
Per division.
Okay, and mathematically, what's that work out to, Brad?
That's 12.
12. And what do I write down here? Because this won't be V peak. This will be what?
VPP.
Yeah, V with 2 P's for peak to peak, yeah? And again, mathematically, what cancels here are divisions. So you simply have 4 times 3, which is 12 volts peak to peak. And that would be a valid way of counting your volts peak to peak. An alternative way of calculating your volts peak to peak is simply double your peak value. So if you're happy with 6 volts peak as being the peak, then you double that, and that will still give you 12 volts peak to peak as well. So either method is valid. You can count the number of squares from the positive peak all the way down to the negative peak, and that was 4 squares, times your vertical scale, and that gave us this value. Very good. Excellent. Thank you. The next question goes to Yusuf. How do we determine our VRMS? What method do we use to determine VRMS? Yusuf?
We multiply our peak by the square root of 0.5.
Okay, we multiply the V peak times the square root of, and got to make that decimal point here, 0.5. And so we have a V peak value of 6 volts peak, and we're going to multiply by the square root of 0.5. I made a recommendation as to how best to calculate this. Do you remember where we start in this calculation, Yusuf? How do I start this calculation, Yusuf?
What do you start with the square root of 0.5?
Yes, I would recommend starting with the square root of 0.5. There's your square root of 0.5. Hit equals so that you can see the 707,106. So you can see that. Once you have the square root of 0.5, then multiply by your volts peak, which is 6 in this case. And what is your calculation, sir?
4.24 volts.
How many people agree with 4.24 volts? What do I follow the volts with, Yusuf? I need to follow it with some kind of subscript here. It's not peak. It's not peak to peak. What do I write down here?
What do was it? Root mean square, RMS.
Yeah, so I write down RMS, and I hit equals, and lo and behold, does the calculator show me 4.24 VRMS? Is everybody consistent with that calculation? Everybody okay with that? Okay, thank you, Yusuf. The next calculation will be for V average. So for V average, how do we go ahead and do that? The question goes to Wei-Ji. How do we calculate V average? What was the method that I gave you last time?
So we use the V peak times 2
So
divided
2V
by
peak
pi.
divide by pi. Okay, so 2V peak divide by pi. And so when we do that, we'll clear the calculator. So 2 times the V peak of 6, and then divide by the pi key, which is a second function, a shift function on your calculators, shift pi, and you can see the pi appears. And so before I hit the equal key, what is it that you calculate, Wei-Ji?
3.82 V average.
How many of you agree with 3.82 V average? Okay, very similar to the exercises we've done in class, yes? And if I hit equals to confirm on my calculator, yes, it's 3.819, and then that 9 compels us to round this to a 0.82. So that was correct rounding. Yes, everybody good? All right. The next value is period. Now, period had a very special definition. What did you write down in your journals for the definition of period? How do you describe to your middle school cousin what is period with respect to this AC waveform? What do you have in your notes, Jacqueline?
The time for one cycle.
Time for one cycle. Okay, time for one cycle. And did I draw one cycle on this particular illustration? It looks like, yeah, I have a starting point right here, and it comes up to a positive peak. The waveform rotates to a positive peak. It rotates down to the 0 line, and then it switches over to the negative side, so it continues rotating. What word am I using? Rotating. The waveform rotates to a negative peak and continues rotating until it goes back to 0. Once it hits 0, it will now begin to do what? It will begin to repeat itself, yes? So one cycle is defined as the time for a waveform from a starting point through its rotation to another point where it begins to repeat itself. So one cycle would be from here all the way up to the positive peak to the 0. This point is not the repeat point. This point is not the end of one cycle because it switches from positive half cycle to negative half cycle. So we've got to follow its rotation to a negative peak until it comes back to 0. So from here to here is one cycle, and the time for one cycle is called period, and period is represented by the symbol capital T. And so how do we determine this particular value, Robert Benavides? How do I determine period? How do I count the time for one cycle?
You count horizontally.
Okay, we count horizontally from here to here. And how many squares do you count for? How many divisions do you count from here to here?
4 divisions.
Okay, so we have 4 divisions. And what do we do with the 4 divisions to calculate the time? Something having to do with this, yes?
By the
Didn't catch.
scale.
By the H scale, yes, because the horizontal scale tells us how much each of these blocks is worth horizontally. So that means one of these blocks, one of these divisions,
You multiply
is
the
worth
H scale.
120 microseconds. So what I'm going to do is I'm going to take 4 times the 120 microseconds. Is that what you're suggesting?
Yes.
Since there's 4 squares. Okay, so we will go ahead and multiply by 120 microseconds. And if you go to do that, let's all do that calculation together, everybody. So we're going to take 4 We're going to multiply by 120 micro. Now, how do I key in micro? Micro is what power of 10? It's going to be an exponent what? Class.
6.
-6.
Is it positive 6 or negative 6?
Negative.
Yeah, because micro is a negative 6, and we have to say negative 6. So here's your change sign key. I'm going to hit the negative. We see the negative appear. We hit 6. Now I have 4 times 120 microseconds. Before I hit the equals, could you give us a calculation on that, Brad? What is 4 times 120 micro? What did you calculate?
I got 480 micro.
Time is measured in units of? Look at your H scale. Look at your H scale up here. The H scale was in units of microseconds, so this works out to be 480 microseconds, which is a lowercase s. Is everybody okay with that value for 480 microseconds? So far, so good? Excellent. Okay, now let's continue. The next thing that we're going to need to determine is the frequency. So how do I determine frequency? Question goes to Yusef. How do I determine frequency?
Frequency is equal to the reciprocal of the time.
Frequency is equal to the reciprocal of time, the reciprocal of period. So once I have period, if I reciprocate that number, the 480 microseconds, I should be able to get frequency. And what is it that you calculate for frequency to be, Yusef?
I got 2.08 kilohertz.
Okay, how many of you agree with 2.08 kilohertz? Raise your hands. Okay, so 2.08 kilohertz. And we're going to confirm that right now. I have from the previous moment, 480 microseconds. I'm going to hit the reciprocal key right there. So it will reciprocate my previous answer. And then I will hit equals. And look at this, it landed on a power multiple of 3, so I don't have to hit engineering. 2.08, and that's a positive 3, so everybody's in agreement. We have a frequency of 2.08 kilohertz. Yes, so far so good. All right. So you would be presented with an exercise something like this. You would have a waveform. It would be graphed. You would have a vertical scale. You would have a horizontal scale, and you need to determine each of those values. So to reiterate, you would be given a V scale, an H scale. You would be asked to look for volt peak to peak, VRMS, the average, period, and frequency. Once we have all this information, we can now take this information back to our schematic and our circuit board, because we can set this up in class. So F is equal to 2.08 kilohertz, and Vs is equal to, we can set this up one of a couple of different ways. We can set this up so that we can measure V peak, and let's go ahead and measure V peak. Vs is equal to 6 volts peak, okay? That being said, now let's go ahead and fill this in. If we determine our voltage source is 6 volts peak, I will write 6 volts peak right here. 6 volts peak. Yeah, let's do it this way first, because we'll do the analysis using Multisim, and then we'll do another analysis using the RMS values. All right, so 6 volt peak, and the RMS equivalent to this that we determined earlier, we had a 6 volt peak and an RMS is 4.24 VRMS. I'm going to write this down here. This is 4.24 VRMS. Just write that down there. All right, we have a series circuit. We have 3 columns, 4 rows, 4 by 3, 12 cells. We filled in the freebies, which are the givens. We're given the resistor 1, resistor 2, resistor 3. This is a series circuit. We determined through our waveform analysis right here what is the voltage, and the voltage 6 volts peak or 4.24 VRMS. How do I fill in the rest of this particular table? Question goes to Wei Ji. How would you begin?
On the total resistance.
Find a total resistance. How many of you agree? Give me a thumbs up. Okay, let's go ahead and look for total resistance. So if we, let's go ahead and use Mama's calculator. 180 and 120. Guess what? There's a 20 and there's an 80. So they combine to give you 100. So 120 plus 180, wouldn't that be 300? And 300 plus 330, wouldn't that be 630? That's just using Mama's calculator, all right? So how many of you agree we should have 630 ohms? Give me a thumbs up. Okay, so 630 ohms. Right there, okay. For currents, we're going to do this things 2 different ways. We're going to calculate the peak current. We're also going to calculate the RMS current. So how do I determine current in this series circuit? What method do I use? Question goes to Robert. What method do I use to calculate current? Ohm's law. So right there, my friends, Ohm's law, V, I, and R. So if I'm looking for the I, what do I need to do, Robert?
Cover the I. So it would be V over R.
Excellent. So V over R. Do I have a V? Yes. Do I have an R? Yes. So let's go ahead and take 6 divided by 630 ohms. Let's do the peak value first. So clear, 6 divided by 630. And what value do you get, Yusuf?
105.
6 divided by 630 ohms?
Wait, 6 divided by 630?
Well, that's our voltage divided by our resistance. So 6 divided by 630.
Oh, 9.52 micro watts amps.
Is it micro?
Milliamps.
Are you sure it's milli? What power of 10 do you have on your calculator?
-3.
-3, and therefore it is milli, yes?
Yep.
Okay, so we could write down this, 9.52 milliamps peak. And I'm going to write this so that this fills half the cell, okay? 9.52 milliamps peak. Before we continue, because in a series, we know something is very special with a series circuit. Before we continue, what should we do with this current calculation? Shouldn't we do what, Yusuf?
Fill in the rest of the current column.
Okay, before we go to fill in the rest of the current column, what would be the prudent thing to do
You want us to
that
double
you
check?
all did during? Yes, we want to double check, because if we made an error here, we'd be copying an error straight up, yes? So let's take a moment and just quickly recalculate. We can do that. Take 6 divided by 630. Lo and behold, we're happy it's 9.52 milli, yes? All right, so 9.52 milliamp peak, 9.52 milliamp peak, and 9.52 milliamp peak. Let's calculate the RMS version of the current, okay? And to calculate the RMS version of current, we still use Ohm's law, except we're going to use the RMS voltage. So instead of using 6 volts peak divided by total ohms, we're going to use 6.24 VRMS divide by total ohms. So Jacqueline, could you walk us through the calculator steps for that, please?
So 4.24 divided by 630 gives us 6.73 milliamps.
Okay, so we will do the 4.24 right there, divide by the 630, and that gave us our, as you called it out, 6.73 milliamps. Does everybody calculate and confirm that value? Did you take 4.24 divided by 630? Does everybody confirm that? Give me a thumbs up, please. Looks good. Okay, I will write this down. 6.73 milliamp RMS. And since we know current is the same, should we fill this column in with that value of current, Jacqueline?
We should double check it first.
We should double check it first. That's the prudent thing to do. Yes, everybody hear that? Don't just fill it in, double check it. And it's easy to do. We just take 4.24, just punched it into the calculator, hit divide by 630, and boom. Are we confident we can write down 6.73 milliamps through the entire column? And we have to write it out, 6.73 milliamp, and you have to make sure it's RMS. 6.73 milliamp RMS. 6.73 milliamp RMS. Everybody okay with that? So far, so good? Cool. Now, we need to determine our voltages. And how do we determine our voltages? Question goes to Robert. How do I determine voltage in this table? What method do I use?
Ohm's law. So
Ohm's
you
law.
would do I times R.
Yeah, cover the V and I would have I times R. So let's calculate our peak voltages first. So in order to calculate my volts peak across R1, I would multiply my peak current times my ohms, yes? So everybody, let's go ahead and do that calculation. Let's take 9.52 milliamps. How do I key in milli? Exponent -3. Is that what I have? 9.52 milli. And now I'm going to multiply that by 180. And the calculated result on this, Robert, works out to be what value do you calculate, my friend?
1.71 volts. Volts peak.
1.71, and we make sure that's a volts peak.
Volts
Yes?
peak. Yeah.
Excellent, excellent, excellent. That's great. All right, fantastic. We now want to calculate the volts peak for R2. And the volts peak for R2, Brad, walk us through that. What are we going to do? Clear the calculator. If I want volts peak for R2, what do I need to do?
So you would do 9.50. Wait, I'm sorry. You would, yeah, 9.52 milli.
Milli, so it's exponent -3. So now I have milli. What do I do with that?
And then you multiply it times 330.
Times 330. And what do you calculate as a result?
I got 3.14 volt peak.
3.14 volts peak. Everybody give me a thumbs up if you agree. Looks good. All right, one more value of voltage. Yusuf, let's wrap this up with volts peak for R3. How do I do the volts peak for R3, my friend?
9.52 times 10 to the -3rd.
Okay, 10 to the -3rd right there.
Wait, 9.52.
Yeah, that's my milli, 9.52, sorry. I'm getting dyslexic here, 9.52, exponent -3, cool. Then what?
Times 120.
Times 120. And what do you calculate, my friend?
1.14 voltage peak.
Okay, and everybody agree, 1.14 volts peak, yes? So far, so good. All right, now we have the peak values. we're going to do the RMS values. All right, so for the RMS values, again, if I'm looking for voltage, I cover up the V, and V is equal to my I times my R, okay? And so that being said, let's go ahead and calculate the RMS voltage for R1. So WG, what do I need to do here?
So you key in 6.73 to the
73
10 to the -3 power,
to the -3, so that's my milli,
and then times 180.
times 180. And we get what value?
1.21 voltage RMS.
Okay, and we have to write it all out, just like what you're seeing here. 1.21 VRMS. And notice I'm using slightly different color. Keep voltages in green, keep my currents in red. Excellent, good. Now we're looking for VR2 RMS. Yusuf, can you walk us through that, please? What do we need to do here?
To multiply our RMS voltage current by the resistance.
Okay, and those values are?
6.73 times 10 to the -3
Mm-hmm.
times 330.
0.73, -3, and we're going to multiply this by 330. And what value do you get, sir?
2.22 volts.
And we should agree 2.22 volts. So write down 2.22 volts RMS. Good. And we have to speak it. We have to write it down. Very good. One more, and we're done with the table. And could you go ahead and do that one for us, please, Jacqueline?
Yes. So 6.73
6.73
exponent -3
exponent -3
times 120.
times 120. And what do you calculate as a result?
807.6 microvolts.
Mm-hmm. 807.6, is it microvolts?
Oh, sorry, millivolts.
Millivolts, okay. Millivolts, RMS, no less, okay? So 807.6 milliV RMS. So now we have a table full of peak voltages, peak currents, RMS voltages, and RMS currents. And the reason why we want to have this table filled with both versions is because the oscope is going to show us the peak values, whereas our digital multimeters will show us the RMS values. Because keep in mind, the oscope is designed to show you waveforms, and it will display the measurements in the form of a waveform, whereas your multimeter cannot do this. Your multimeter can only give you a singular digital value, and that singular digital value would be the RMS version of that waveform, which we should be able to verify as 4.24 VRMS for our source. We're going to do that next week because you're going to build this circuit. So this circuit, my friends, looks like this guy here. We have, move this aside, we have the 180 ohm resistor, we have the 330 ohm resistor, we have the 120 ohm resistor. This is coming off of the power rail feeding the first resistor. First resistor connects to the second resistor connects to the third resistor connects with a set of jumpers down to the negative rail, and we will just simply hook up our power supply right here and call it a day, yes? And so this guy will, well, actually, no, we won't be using the DC power supply. We're going to be hooking up an AC generator to this from our workbench. What you're going to be doing are a couple of things. What I'd like for you to think about here is this. If we take this circuit and I am asking you for voltage at A, voltage at B, voltage at C, and voltage at D, how do we make those determinations? If I want, let me use a different pen, VA with a single letter subscript means I happen to have a red probe. So here would be my red probe. And I would have a black probe. And let's say here's my black probe. And so how do I connect these if I'm just given that singular letter of VA? How do I go ahead and do this? Question goes to Yusuf. What do I do here?
Do you need to tap in between the voltage, the positive side of the voltage source and A? Or you want to do math?
Well, I would like to do voltage at point A when I'm shown a single letter, but I have two probes. Where do I hook each of these probes is my question.
I guess you put the black one at the point between R1 and A, and then put the red one on A.
Well, if I put this between R1 and A right here, and I put this one at A like that, I'm physically measuring the same point. This is only a piece of wire between the tips of these two probes. So what do we do when we see a singular letter? Who recalls? Jacqueline?
You put the red probe on the letter and you put the black probe on ground.
Okay, if you're only shown a single letter like this, you put the red probe on that letter, where the red probe is on A, and the black probe goes to ground like this, okay? And what do we expect to measure between A and ground in this particular case, Jacqueline?
Would we be measuring 2.08 kilohertz?
We would measure that frequency, yes, but what is the voltage we would measure? Frequency, you're correct, is 2.08 kilohertz. What is the voltage I would measure between these 2 points?
6 voltage peak.
Okay, so I would expect to measure this. I would expect to measure 6 volts peak, and I would also expect to measure 4.24 VRMS. So if I set my measurement to measure peak, I expect to see this value of peak. If I set my measurement to measure RMS, I would expect to measure this value of RMS, so 6.24 VRMS. Now, let's go ahead and take for a moment, let's go ahead and write the rest of these values onto our schematic. Across this particular guy, from here to here, we calculated 1.71 volts peak. Across from here to here, keep everything in peak. So we calculated 3.14 volts peak. And then across the last guy, 1.14 volt peak. Okay, all of these peak values of voltages come directly off of our table. 1.71 volts peak across R1, 3.14 volts peak across R2, and 1.14 volts peak across this guy. Now we know that the AC waveform does at some point in time, certain times, we happen to have a positive half cycle right there, and at other points in time we happen to have the negative half cycle. So it switches back and forth between these two. Let's go ahead, just for the sake of this discussion, let's polarize this for the moment at positive on top, negative on bottom. How would you polarize the rest of these resistors based on this polarity on the source? You want to treat this, the way I've drawn this, as if it were a DC source for a moment. You want to treat it like this. That, at this moment, is positive on top, negative on the bottom, okay? Because we're only looking at the positive half cycle. That being said, this lead of R1, which is closest to the positive side of the source, shares that polarity. So this side of the resistor should be what polarity? YG?
Positive.
This side should be positive, and the side over here should be negative. So that sets up the polarity pattern for the rest of your resistors. So moving away from the source, watch the pattern. This is positive because they are next to each other. And then the pattern is set up as positive, negative, and then this is positive, and then negative, and then this is positive, and this is negative. And do I have the negative lead of R3 connected to the negative side of the source? Yes? So far, so good. Now, the question then becomes, what do I expect to measure at point B? The voltage at point B means the red probe goes where? Single letter, looking for voltage, here's the red probe. Brad, where do I put the red probe if I'm measuring the voltage at point B?
The red probe will go on the positive side of the resistor number 2.
It would go on point B. Simply goes to point B, and you described it correctly. All right, right, okay, right there. And then where does the black probe go?
Point C.
If there's a single letter here,
Uh,
where does the black probe go?
At the end of at the ground? No.
Ground, yes, yes. If there's only a single letter presented, the black probe will always go to ground. So this is ground here. Isn't this ground over here at this end of the wire? It's the same. And isn't this ground all the way to point D, yes? So G and D are electrically the same, yes? We could state that. I can also write that out. I can say points G and D are electrically the same. Okay, they are electrically the same. So if you're only shown a single letter, red probe will go to that single letter, point B, and I have the red probe at point B. There's no designation for the other point. That other point will always be ground. And this ground point right here is electrically the same as this end of the wire, which is electrically the same as this here. So my question now, Yusuf, what am I going to measure between these two probes? What value would I have here? How do I determine this value?
They're going to be added together.
What's going to be added together?
The voltage of resistor 2 and resistor 3.
So your classmate is suggesting that this voltage across R2 and this voltage across R3 are going to be added together for the total voltage between these 2 points. So Yusuf is going to add the 3.14 plus the 1.14. So what does that add up to be in terms of volts peak?
4.28 voltage peak.
4.28 voltage peak. Does everybody agree to that when you add those two together? All right, so far so good. What would that value be in terms of RMS? The voltage at point B in terms of RMS. Well, let's go ahead and write the RMS values in here. This resistor was 1.21 VRMS. This resistor was 2.22 VRMS. This one was 807.6 milli VRMS. So how do I determine this value of voltage between point B and ground in terms of RMS values? Wei-Ji, how do I do this? Yeah, I'll repeat the question. The question is, I'm looking for voltage at point B, but I now want the RMS voltage, VRMS. How do I determine this?
Just the 2.22 VRMS plus the 807.6 milli VRMS together.
So I'm going to add this RMS value of 2.22 VRMS plus this value of RMS voltage, 807.6 milli VRMS, And if we go to do that, what does this total out to be? Wei Ji, do you have a calculation for that? We clear 2.22, and we're going to add the 807.6 milli. What do you calculate this to be?
3.028. 3.03.
Okay, we would call this out as 3.03 VRMS, yes? Okay, for voltage at point B. Very good. And now we have another point to reconcile, and that is voltage at point C. So the voltage at point C means, how are we going to do this, Brad? Robert, your turn. What am I going to do? Red probe goes where, Robert?
So red probe goes to point C, and then black probe.
Okay, red probe at point C. Where's my black probe going to go?
Goes to ground.
Ground, which is the same as this corner wire, which is the same as D, yes? So how much voltage do I have between these 2 points, my friend? What's my peak voltage between these 2 points?
4.
Okay, so I have 1.14. Yes, 1.14, and you want to say volts peak. Okay, it's not just 1.14, it's 1.14 volts peak. And what would be the RMS value of voltage between these 2 points, Robert?
107.6 RMS.
0.6 what?
RMS.
Millivolts RMS, yes?
Oh, millivolts.
Millivolts RMS. Okay. And we can double check this. Check this out, everybody. Everybody right now, if I want to confirm this RMS value based on this peak value, do this with me right now. Everybody take the square root of 0.5, square root 0.5 equals, and now multiply by 6, times 6. And what do you calculate? What does your calculator show you when we do this, Brad?
I got 4.24.
Which is what we wrote down here, right?
Yeah.
All right, so now we're going to confirm this number. How do we do that? The way we do that, everybody right now, take the square root of 0.5, square root 0.5, it equals, and now multiply it by 4.28 volts peak, right here. Multiply by 4.28 volts peak, so times 4.28 volts peak. And Yusuf, what do you calculate for the RMS value?
Sorry, you're doing the 707.
Yeah, times this peak voltage of 4.28. What do you calculate for the RMS?
Calculations. Sorry, I was doing
Okay, well, you gotta hang with us, okay? So what we're doing is we're verifying these values of RMS strictly on the peak voltages, okay? So we verified using square root of 0.5 times this peak, gave us that value of RMS. I'm asking you to do the square root of 0.5 times this value of peak. So there's my square root 0.5 equals, and now multiply this by 4.28. What is your result?
3.02 voltage RMS.
Yeah, but if you look at your calculator,
3.03. Sorry.
and have we verified, and we're happy with 3.03 VRMS. We have one more to do. Let's go ahead and do this one. Everybody take the square root of 0.5 equals, and now multiply by 1.14. 1.14. Square root of 0.5 equals, and now multiply by 1.14. And when I go to do this, the calculated results, Wei Ji, works out to be what?
806 milli VRMS.
Did we do something different? We had an 806. Oh, okay. The reason why there's some slight differences because we used rounded off values for current and rounded off values for voltages. We're in the ballpark. All right. So that being said, now what we're going to do, we're going to take this information and we're going to go into Multisim. So I'm going to switch up our screen here in just a moment. And we will go to Multisim, which I have over to here. So let's go ahead and share my Multisim screen right there. I'll go ahead and share this one right here. Can everybody see my Multisim? Give me a thumbs up if you can. Cool. You have Multisim. So I'm going to log in. And this will recognize me in just a moment. And enter my password for I'm a sample. Log in. And we're going to build this circuit. So create a circuit. We come over to the left-hand side and we see an AC voltage source. I click on this and I want AC voltage. Click and I want to place it right there. Now I have an AC source. Double click this guy and I can now enter the parameters. So my voltage, I can select to be peak voltage or I can select RMS. Let's stay with peak for right now. And so if I select right here, here's where you make the selection, this little pull down, peak versus RMS. If I want RMS, I would do this. If I want peak, I would do this. Okay, so I'll keep it at peak. And the voltage at point A, the default is 1 volt, but I'm going to make this particular guy 6 volts peak. So I'm going to enter 6. And the frequency, the default is 1 kilo, but I'm going to enter 2.08, 2.08, and enter lowercase k, and enter. So now I have 6 volts at 2.08 kilohertz. I can now deselect and my AC source is set. I will go ahead and come over to this side and grab a resistor. I want a resistor and I will place it, one right there. And this first resistor will be 180 ohms. So I will select and hit 180 and hit enter. So now I hit enter. Okay, good. Do I now have 180 ohm R1? Everybody happy with that? I'm going to click resistor again, place a second resistor right here, and come over to the value, highlight this, and type 330, and hit enter, and deselect. Now I have an R2 that's 330 ohms. I'm going to come over here again, select this tool, select resistor, place a third resistor right there, and select the value and make this particular guy 120 ohms and deselect. So now do I have my voltage source and my 3 resistors? So far so good. I'm going to get my probe and see, right now it's a hand, but the moment I get close to, ooh, I had it there for a moment. This will turn into a spool of wire, which will allow me to make a connection. It's a little hard. I'll do it from this side. Come on, mouse. I'm going to make this bigger so we can see this better, and that might help my graphics. Everybody see this nice and big? Is this better for you now? How about this? Okay. Bring my mouse over here, and it will become a spool of wire, right there. Click and drag down and click. There, I have a connection. That's wire number 1. If I don't like to see the label there, I can come over to the right-hand side, pull down on display, and uncheck the checkbox net values. The moment I uncheck this, this 1 will disappear off of that wire. I'm going to take the 1 off because it is distracting. Deselect. Deselect means I'm clicking somewhere other than the components of the circuit. Come up to here, wait for my spool of wire, click and drag, connect. Come over here, deselect net values, deselect. Come over here, wait for my spool of wire. Be patient. Deselect, come over, spool of wire. There it is, connect and click. Shows a number 3. Again, that's distracting. Select the wire, click net values. Now there's no more number on the wire. I do need to complete the circuit, so I'm going to come over here, wait for my spool of wire. There, and come down to here, come over to here, click, and come up to here, click. And that's labeled wire number 4. Again, deselect. Now I have a really nice drawn circuit so far. And one more thing I do need to add is my ground. So come over here, select this, and I do want ground. So select ground, and I will go ahead and place a ground right there. And my spool of wire, I will make a connection. I have a node. Looks pretty good so far, yes? Now, I'm going to place my voltage probes at very specific points. I come up here, and I want voltage, so click on voltage, and I'm going to place my first probe with the tip right at that corner. Isn't that A? Okay, and I'm going to make this PR1. I can label this label this point A. Enter. And deselect. And bring in another probe. And go ahead and place it right here between 2 and R1 and R2. And label this point B. I cannot have a space in here. So point B, and hit enter. Good. And do one more here, voltage, and click right there. And let's make this point C. And we'll do one more. Click here and place voltage at this point here, and we will call this point D. Point D, enter. All right, deselect. So is my circuit nicely built? I think at this point in time, we've done so much work. We ought to do this. Let's come up here and let's do a save as. And I'm going to name this circuit oops, come here. Make sure I'm selected. So AC series 3R I'm a sample. Cool. There. That way, if I mess up, it's I'm a sample's fault. It's not the co-guy's fault. All right. So do we have a title here? AC series 3R, 3 resistors by I'm a sample. And now everything is set for us to do a simulation. So I'm going to hit split. So here's the split. So I have a split screen. And you notice here is waiting for data. I'm going to hit minus one more time so I can see my schematic on this side. There's my schematic right there. And when I go to hit play on my simulation, when I run my simulation, I'm going to have an O-scope display showing each of these points in the various colors. Point A will be the green graph, point B will be the blue, point C will be the violet, and point D will be magenta. Watch what happens. Click. It's running, it's loading. All right, lots and lots of waveforms happening. So right now, the waveforms are pretty close together. That's very hard for us to read any kind of information. I'm going to hit a pause on this for a moment so it stops the jiggling. And I'm going to scroll down here on this side and change. Let's take a look here. I think I'm going to need to have this in the run mode before I can do the change. So do the run, and then, yes, I now have my time per division. So with my time per division option on the right-hand side, if I click in this direction, have I widened the space between the waveforms? Yes, because I got too many cycles on the display. So I'm going to hit this guy and this guy one more time, and that's good. Now I'm going to hit pause. Clink. Now I have a pause. So now do I have not many cycles, 2 complete cycles looks like, right? I have from here all the way up to positive peak, negative peak, and it looks like I've got 2 complete cycles on the display. Now check this out. Does the green waveform show us in here that this is connected to point A and this is my very first voltage? Did we confirm that this is a 6-volt peak? Yeah. And is this peak right on the 6-volt line? How about that? We can bring in cursor. I could bring in cursors right here, and let's cursor on the y-axis. What did I do? I selected cursors. This is no cursors, so there's no lines. Cursor means I'm going to bring in some horizontal lines or vertical lines. So I'm going to select cursor, and I want this on the y-axis, which means I'm going to get horizontal cursors. I can now come over and grab this cursor and move it to the tippy top of my green waveform, right there, as much as I can approximate. And does it show cursor 1 at 6.0104 volts peak? Pretty good. What did we predict our volts peak for our point B? Point B was 4.28 volts peak, was it not? So I'm going to move cursor number 2 to the tippy top of the blue waveform, as close as I can get it. And it shows cursor number 2 very close to 4.28. This is actually 4.297 is where I happen to place. And is that pretty good, pretty close to my 4.28 volts peak? Pretty darn good. And I've got one more waveform at point C. And we said point C should be 1.14. I'm going to go ahead and move this one down to the tippy top of point C, which is the deep purple one. And it looks like, put this right in the middle of that waveform if I can. Ooh, had it there for a moment. Okay, that's pretty close. We expect 1.14 volts peak, and what does it measure for cursor number 2? 1.17. Pretty darn close. So what it is that you're going to do as a deliverable for this task, there's 2 parts of the deliverable. One part of the deliverable will be to create the multi-sim circuit. The multi-sim circuit looks as what I've just done here. It must have a title, AC Series 3R by your name, not I'm a sample. So it would be Brad Diaz, Robert Benavides, okay, Jacqueline Tay. It would have your name, and you would show the 3 voltage points exactly where I've placed it, and it should show you the 4 traces. The purple one being, the magenta one being 0 volts because that point is ground, okay? As you can see there, it's ground. And it's supposed to be 0. So I have all 4 traces, and and all 4 of these are correct. So you need to do a freeze, a pause, if you will. So here's the run. And while it's running, what did we do? While it's running, you want to scroll down. Simulator options, and we had it here for just a moment. Stop. Do the run again. Simulator loading. Okay. When it's running, you want to have the menu option time per division. And time per division, when this thing starts, didn't it start with a lot of waveforms that you couldn't begin to read? Right. So how did we make this into 1 or 2 cycles on the display? You punch play and stop until you see this as an option, time per division. And when you're on time per division, you click this on the left-hand side until you see just a few cycles on the display. Now, if I stop it at this point, do I still have too many cycles on the display? Now, I got 1, 2, 3, 4 cycles on display, too many. I need to run it and probably click this one more time. If I click it too far, watch what happens. Oh my goodness, I can't even see one cycle. So this is useless to us. I have to see at least one, if not more than one. So what do? Put it in the run mode and adjust my time per division so that I get something that allows me to see at least one, if not 2 cycles on the display. Hit the pause, run, hit the pause. Okay, hit the pause. Okay, that's a nice picture. I just need to see at least one full cycle, and then anything more than one is fine, but I see one. And so what did I do next? Cursors, remember, it starts off with no cursors. So what you need to do is, there's a cursor control right there. There's axes control. So you want to open the switch on cursors, and then on cursors, you want to select from none to the y-axis. And once you have cursors on the y-axis, you have these green lines. And what you want to do is you want to place cursor 1 right at the tippy top of your waveform. And we said it would be 6 volts peak, and does cursor 1 show 6 volts peak? You place cursor number 2 at the tippy top of the blue waveform. We said it should be 4.28 volts, 4.269, it's almost 4.27 volts, pretty close. You're going to do a snip. Watch how we do a snip. Here's my snip tool. Select the snip tool, and my snip tool is here. Here's my snip tool. Select new. Now, the moment I select new, everything will go gray. I now move my cursor, my crosshatch up here, and select all of this. I don't need anything past the graph, but I do need the values at the bottom of the graph. And I do need the schematic. I do need your name and the title. Select. So this is what you're going to paste into a Word document to upload. Do you see AC Series 3R by, it'll be your name. Can you see your circuit built this way? And can you see the waveforms this way? And so what you're going to do is when you have this in your snip tool, you will select Edit, Copy, and then open up the Word document. Bloop, right there is the Word document. Hit blank document. Can you see my Word document?
I don't think we're seeing, am I not seeing it? Is everybody else seeing it?
So, no, yeah, let me go to a different share. Let me go to share my computer screen as opposed to the this screen. So here, let me go to share, and I'm going to go to this window. Then you can see other things that are happening. All right, so let me close the Word and close the snip. Don't want to save changes. So here is my multisim as you saw a moment ago. I come down here to my snip tool. Snip. There's my snip tool. Hit new right there. You can see there. And see my crosshatch. My crosshatch tool comes up. Select from this corner all the way to the graph to the bottom of the values. Can you see the numbers below cursor 1 and cursor 2 at the bottom right of the screen? That's where your snip boundaries need to end up. If once they're here, you let go of the mouse, and did it capture your name? Did it capture the circuit? Did it capture all the values? You come up here to Edit, Copy, and then you open up a Word document. So I will open up a Word document. And blank document, like so. And then Control V. Did you write that down? Control V. Or you can also right click and hit paste. That works also. All right. So is that pasted onto a Word document so you can validate that you have built this in Multisim? And what you're going to do is you're going to here, File Save As, and this will be in our class. This will be our WK-6 AC3R, or Series 3R, AC Series 3R. Click here. Series 3R by your name. Okay, and then you hit save. And so once you save that, that's what one of the things that you'll be uploading, all right? So we've just gone through a circuit analysis on paper. We've gone through the analysis of using Multisim to verify these values. Let's go ahead for a moment. And come back to our Multisim. And as we're on Multisim, let's go ahead, hit the stop button. And while this is on the stop button, I'm going to select right here, scroll up, and on my sim, run and sim. Okay. Before I do my sim, let's hit stop. Okay, sim settings. No, we're fine there. Sim, logic levels, sheet. No, okay, I think this is good. The other one that you're going to do will be this circuit. So let's go back to tape off this share screen. Are there any questions regarding how to set up your Multisim?
So there's only 2 cursors. There's not a third one.
This gives us 2 cursors, and what we're going to do is we can move this cursor down from here to here just so that you can verify your voltage at point C, and it was supposed to be something close to 1.14, and I'm just a little bit below the crest. I'm at 1.1192. So yeah, to answer
But
your
when we turn in the
question,
screenshot, there will only be 2 in the screenshot when we turn it in.
that's right. Yeah, that's all you can do is just show me for the peak voltage, but you can move this to that position and verify so you can feel good that yes, that value of voltage on your screen is close to what it is we asked for it to be, which was 1.14 volt peak, okay? So it doesn't matter where your cursor 2 ends up, whether it's on the voltage at point B or the voltage at point C. I leave that up to you. Cursor number 1 has to be voltage at point A, which is the top of our green waveform. All right, did that answer your question, sir?
Yeah.
Okay, so what we're going to do is when we leave the circuit built, okay, when you come in on Monday, you need to leave the circuit built because we're going to hook this up to a real function generator and a real oscope and digital multimeter, the whole 9 yards. And we're going to verify all of these things that we've calculated using real instruments. So we will verify our current in RMS by using a multimeter. Each one of these we will be able to verify by breaking the circuit open in different places. And we will verify the frequency using the oscope. We will verify the peak voltage by using the oscope. We will verify using the oscope at point A, B, C, and D. And you'll be able to verify all of the waveforms that you've done to Multisim on the oscope as well. The other circuit that you're going to be building, now since I'm using half circuit boards, you can build this very compactly for half of the circuit, and then the other half of your circuit board, since you have nice long circuits, you're going to be building a parallel circuit. And your parallel circuit will look something very similar to what we've done in the past. So here we go. Here's your parallel circuit. You will have different resistors for parallel. And for parallel, let me show you what it is that you're going to be building. And let me go ahead and do this. This will be right here, AC voltage source. And here we're going to use a different frequency and a different amplitude, but the circuit will look like this. Here to here, here to here, and here to here. And you have these resistors as well, and I'm going to ask you to do your R1 as 220 ohms, your R2 as 100 ohms, and your R3 as 330 ohms. So you have these resistors, the first set in the large ones that I've given you, and the second set can be the small ones that I've given you or that are part of your kit. And so when you go to build this, it'll look very similar to this guy right here that we built before. I'm going to connect this guy up here, and there would be your parallel circuit. We would have R1 of 220 ohms, R2 of 100 ohms, R3 of 330. We're going to have one leg jumping from the positive rail to this point, and we're going to bring the top of these connected together using the jumpers, and then each one of these going to ground. So this will give us measurement points for current, yes? All right. And so couldn't you have both of these built into a singular circuit on your long board? Yes. And you want to leave these in place because in one instance, we're going to be measuring voltages and currents on the series circuit. And in the other instance, we're going to do voltage and currents on the parallel circuit. So on the parallel circuit, what it is that you need to do is a VIR chart as well. So VIR, we won't do that now, but you will do this before we meet on Monday. So you have R1, R2, R3, and totals. And then you will have these guys here. And then this will be 220, 100, 330, and you'll figure out what the RT is. Now the voltage will be this. I'm going to select VP is equal to 7 volts peak, and my T, I'm going to do F. F is equal to, I want to say, 3.5 kilohertz. So those will be the parameters that you're going to be using for this table analysis, and those will be the same parameters that we will be building in Multisim. So using these parameters, I'll show you how easy it is to set up in Multisim. I'm going to come back to our share screen. So come back here to share. And in the share, I want this one here, screen 2, and hit share. All right, so now you're looking at my screen 2. So I'm going to come up here and make sure I save this one. Boom. And it's saved. And come up here, and I'm going to do new file. And on the new file, I'm going to grab my AC source, click, and AC voltage, and boom. And double click, and this particular guy will be a 7 volts peak, because I'm using peak voltage, and the frequency will be 3.5 K. And then I'm going to come over and select one resistor and place. I'm going to select a second resistor and place. I'm going to select a third resistor and place. Select the first resistor, rotate, and move this over just a touch. Good. Select the second resistor, rotate. Select the third resistor, rotate, and move it over just a touch. Select the first resistor, double click, make this 220, enter. Second resistor, make this guy 100 ohms, enter. Select the third guy, make this 330 ohms, enter. Now we're going to connect all of this. So my wire, click, come over, click, come down and make a connection, click, good. Take off my display. Second resistor, wait for my spool of wire. Come on, spool of wire, work with me. Nope. It's being fussy. I know. This will help it be less fussy. This helps. So come over here. There you go. There's my spool of wire. Come on. There, come up, click, and make the connection there. And then do the same thing here. Spool of wire, come up, click, make a connection there. And deselect spool of wire. Come down here and come down to here, come over to here and come up and click. That's good. I don't want the value on that. And then deselect and come over to here, spool of wire there, come down and click, deselect, come down here, spool of wire, click, and there. And the last thing is let's bring in a ground. Ground. There, deselect, spool of wire, and make a connection. Cool. All right, so guess what we're going to do? You've got it built, and you've got AC going on here. And if you're going to bring in a probe, wow, let's bring in a probe and let's place one there. Let's bring in another probe, place this one here. Let's bring in another probe, place this one here. Let's bring in one more probe, place this guy right here. And you would label these points A, B, C, D as you did before. Now check this out. This is very interesting because if I go to split my screen and I go to run my simulation, what do you expect to happen? Dude, should we see different heights on our waveforms? Jacqueline, what do you think?
I don't think we should.
What do you think we would see?
I think it might just be a straight line, like DC voltage.
Okay. You think it might be a straight line. Wei-Ji, what do you think?
They're gonna be four same line, looks like the same.
Okay, so four superimposed on each other. Here, I'll show you what happens. Check this out. This is really cool. Okay, so when we see this many, we know we have to make an adjustment on time, yes? So time. Interesting. Pause. Wow. Where's my green trace? Where's my blue trace? Where's my dark purple trace? Where's my magenta trace? They're all superimposed on top of each other. Why is that? Why are they showing the same amount of voltage? Because in a parallel circuit, isn't voltage the same? Yes. So this is all we can expect to see when we build a parallel in Multisim and show the waveforms. They're all there. except they're all combined together. When you combine them all together, the two darkest colors will overtake everything. We end up with a deep purple by the time everything's combined together. So what you're going to do is you're going to label this. Let's go ahead and label this, and then we can wrap this up. This will be AC. Oops, come back here. Come on. AC. It's delete. Gee, it's not pink. Come on. Don't make this difficult for me. Aha. AC. Parallel 3R by your name. Okay, can we agree that that's how we'll name the circuit? And that's another screen snip that you're going to do. One more way, one last thing, we'll wrap this up, is another alternative way of doing the screenshot is let's just hit Alt print screen. So if I, on the keyboard, hold down Alt and I touch print screen, boom. I can then go to my Word document, which I've had from before. Open that guy up. There's my Word document. Here's my Word document from before. And at the end of this, hit Enter and hit Control V. Yeah, Alt V didn't work so well. The snip works better. The snip allows me to get just the part of the waveform I want instead of the entire screen. All right, so here, my snip tool, hit New, select this part that I want, edit, copy, and go to my Word document. Get rid of this guy because it's useless, and paste. So now do I have my two snips all in one document? Is everybody okay with all this? Fantastic. I will go ahead and wrap this up then. Say thank you very much. Have a lovely weekend. Any questions that come up, please don't hesitate to connect with me via Discord. And you can keep an eye out for, and congratulations again. Everybody got 100% on that test. So proud of all of you. Good job, everybody. Thumbs up. So with that, thank you and have a lovely, lovely weekend. Adios.